Every discovery on Mars changes how we imagine the red planet, and sometimes the entire future of space exploration. For decades, scientists and dreamers alike have clung to a tantalizing prospect. Mars, cold and barren as it is today, might still harbor liquid water, hidden just beneath the surface, or trickling down its dusty slopes. Liquid water would mean hope for life, and an enormous leap for future human missions. But what if we've been chasing a mirage all along? Picture this: a high-resolution image from NASA's Mars Reconnaissance Orbiter. Across the ochre dust and crumbling cliffs of a Martian valley, a dark streak appears, snaking hundreds of meters down a steep slope. Within months or years, it vanishes almost as mysteriously as it arrived. These odd features, called slope streaks, have been showing up since the late 1970s. Over time, some fade away, others multiply, and the questions only deepen. Were these the footprints of running water? Or were we simply misreading the planet's own dry, restless winds? Today, we're going deep into the high-stakes debate over Mars's enigmatic slope streaks, features that have obsessed planetary scientists for nearly half a century. We'll uncover revolutionary new research that may finally answer the biggest question about the red planet. Is there really any liquid water left on Mars? And what does that mean for the hopes and plans of everyone from NASA to Elon Musk to everyday dreamers of humanity's next great leap? But first, how did we get here? Why did these fading marks on Martian hillsides become the world's hottest extraterrestrial mystery? The story begins in the late 1970s, with the first wave of Martian orbiters sending back detailed images of the planet's surface. Amid the endless deserts, craters, and frozen volcanoes, scientists noticed something strange: narrow, dark streaks running down the sides of cliffs and valleys. They appeared on steep, dusty inclines and seemed to form spontaneously, sometimes even in stretches where nothing else visibly changed for years or decades. No one knew what triggered them. These were dubbed slope streaks, and almost immediately speculation began to swirl. Could they be seasonal flows of liquid water, seeping from underground ice or forming briny trickles on the sun-warmed surface? Or were they simply dust avalanches, set off by Mars's wild winds, meteor impacts, or perhaps even subtle Marsquakes? For a long time, the evidence was frustratingly ambiguous. Mars is a planet where the surface pressure is a fraction of Earth's, and daytime temperatures can swing wildly from -100 to a balmy 0. Water, if it exists at all, must fight through brutal cold and bone-dry air, a place where even pure ice can sublimate directly into vapor. Still, hope persisted. In 2011, NASA's Mars Reconnaissance Orbiter made a bombshell announcement. It had found new seasonal features, shorter-lived and even more mysterious, appearing in spring and summer on sun-facing slopes in certain craters. These recurrent slope lineae, or RSL, seemed to grow and fade with the Martian year. To many, this was the smoking gun for modern-day water. Media headlines exploded. Suddenly, Mars was back in the running as a potentially habitable world, at least in brief windows of warmth. But skepticism never let up. Some planetary scientists pointed out that Martian brines, if they existed at all, would have to be loaded with salts just to remain liquid in the planet's extreme environment. Others countered that the crust was simply too cold and dry flows were a better fit. The debate raged. Were we glimpsing a world with hidden water, a place where biology could get a toehold, or just the dusty size of a dead planet? To answer this, researchers needed more than mere images. They needed data, lots of it. Thermal readings, wind records, humidity maps, and most critically, a comprehensive catalog of these elusive features across the whole Martian globe. Fast forward to the present, and technology has finally caught up with curiosity. In a groundbreaking study published in Nature Communications, a team led by Adomas Valentinas from Brown University and Dr. Valentin Bickel from the University of Bern harnessed the power of artificial intelligence to tackle the riddle head-on. Using a neural network model, the team trained their algorithm on over 1,000 meticulously labeled images of confirmed dark and bright slope streaks, then unleashed it on more than 86,000 ultra-high-resolution photos from the Mars Reconnaissance Orbiter. The result? The first-ever global catalog of these features, over 500,000 slope streaks, mapped and studied in detail. That's more than 13,000 bright slope streaks, and nearly 484,000 of their darker cousins, crisscrossing the planet's ancient hills and modern plains. The statistics are staggering. Bright slope streaks cluster mostly in the oldest terrains, places like the battered Noachian highlands, carved by billions of years of Martian history. Dark streaks, on the other hand, dominate the more recent Amazonian plains, with an astonishing 68% concentrated in a single region. The Olympus Rupi's Lycus Sulci area, at the fringe of Mars's greatest volcano. Some stretch for nearly a kilometer, transforming up to 0.07% of the entire Martian surface over time, a significant factor in the planet's ongoing geological drama. But it's not just about where they appear, it's about why. By overlaying their global map with Martian weather data, the team could hunt for patterns. Were streaks more likely to form on sunlit slopes, where warmth might allow ice to melt? Did they show up after big temperature swings, during spikes in humidity, or in regions known for perchlorate salts? Here's where things get shocking. No direct correlation surfaced between slope streak formation and the factors you'd expect if liquid water, or brines, were involved. Not slope orientation, not sudden warming, not high humidity. Instead, the biggest predictors turned out to be wind speed and dust activity. Where Martian breezes blow hardest or deposit the most fine dust, that's where streaks most often appear. This research marks a significant shift in our understanding of Martian surface processes, says Adomas Valentinus. We're moving away from liquid water as the primary explanation for these features and embracing the role of dry, aeolian, wind-driven processes. Imagine that. Mars isn't so much a frozen water world as a restless land of dust avalanches and gales. The study's modeling even suggests these events could transport millions of tons of dust every year, shaping the Martian climate and possibly rewriting the textbook on Martian geology. But the debate is not entirely dead. As Dr. Christopher Edwards from Northern Arizona University points out, while the evidence strongly supports a dry mechanism, we shouldn't completely dismiss the potential role of subsurface ice. Even if water isn't directly involved, its presence beneath the surface could influence dust behavior and slope stability. There's also the matter of the RSL, those short-lived recurring marks that first electrified the planetary science world in 2011. Alfred McEwen at the University of Arizona, a leading expert on Martian surfaces, remains cautious. Dust avalanches and CO2-driven processes undoubtedly explain many features on Mars. However, the unique characteristics of RSL, particularly their seasonal recurrence, still hint at the possible involvement of briny water. That tension lingers. Is Mars really as dry, desolate, and inhospitable as this new research suggests? Or are there hidden pockets, seasonal tricks, and rare events that still defy our models, places where water, if only for a moment, might awaken under the thin Martian sun? And then there are the implications. If slope streaks and RSL are mostly or even entirely products of dust and wind, what does that mean for Mars missions? For years, planetary protection protocols treated these features as high-risk, potential harbors of Martian microbes, to be explored only with the strictest controls. If they are simply the result of dry avalanches, does that open the door to more aggressive exploration and faster human settlement? Or does the lack of water here mean we need to turn our gaze elsewhere, to buried ice caps or ancient lake beds, in our search for Martian life and the resources essential for colonization? But even as the scientific consensus teeters, many experts urge caution. The SETI Institute warns, regardless of the formation mechanism, we must exercise extreme caution when exploring RSL sites. The potential for terrestrial contamination remains a serious concern, and we need to proceed responsibly. James Ray from Georgia Tech adds another wrinkle. Even if RSL turn out to be dry features, they could still serve as valuable indicators of subsurface water ice deposits. These areas could be strategic targets for future resource utilization efforts. So how will these revelations reshape the next phase of Martian exploration? Will space agencies refocus their search for habitability, shifting away from streaks and towards the deeper mysteries locked in ancient ice and minerals? Might we see new technologies, perhaps dust-resistant habitats or robotic dust avalanche predictors, emerge from this radical revision of Mars's surface processes? Or, in chasing dust, will we miss a deeper, more elusive secret of the red planet, one that could change humanity's future among the stars? The answers aren't simple, but they will shape not just the science of Mars, but the politics, technology, and dreams of our interplanetary future. Stay with us as we uncover what this new science means for the hunt for life, the race for Martian resources, and the ultimate fate of our ambitions beyond Earth. The question looms: did we just lose the last great hope for Martian water, or are we on the cusp of something even bigger? So, with the centuries-old Martian riddle seemingly cracked by machine learning, What does this all mean for the future of Mars exploration and for our dreams of finding life beyond Earth? Let's start with the immediate consequences. This paradigm shift throws the priorities of Martian missions into sharp relief. For years, recurring slope lineae, those dark, finger-like streaks appearing and disappearing with the Martian seasons, were at the center of astrobiological hope. If they had been proof of transient liquid water, then perhaps, just perhaps, tiny Martian microbes could eke out an existence there, sheltered in ephemeral rivulets of brine. But with the latest research stacking the evidence in favor of dry, dust-driven avalanches, the equation changes. Adomas Valentinus, the study's co-author, drives the point home. We're moving away from liquid water as the primary explanation for these features and embracing the role of dry, aeolian processes. For mission planners at NASA, ESA, and other space agencies, this means landing zones once considered too risky or precious to touch for fear of contaminating potential Martian oases might soon open up. It could be a game changer for engineering teams, as strict planetary protection protocols designed to prevent Earth microbes from invading habitable sites might be relaxed, at least in these streak-strewn regions. Yet not all mysteries are resolved. In fact, some new ones are just beginning. If slope streaks and most RSLs are dry, what about the few sites where the seasonal rhythm of RSL seems tantalizingly similar to terrestrial brine flows? Alfred McEwen from the University of Arizona, one of the giants of Martian geology, reminds us, dust avalanches and CO2-driven processes undoubtedly explain many features, but the unique characteristics of RSL, particularly their seasonal recurrence, still hint at the possible involvement of briny water. This tension between dry certainty and damp possibility is more than academic. If even a handful of RSL are shaped by underground brine seeping to the surface, Mars could still hold isolated pockets of habitability, potential refuges not just for life, but for future human explorers who may one day rely on indigenous water resources. James Ray of Georgia Tech notes, even if RSL turn out to be dry features, they could still serve as valuable indicators of subsurface water ice deposits. These areas could be strategic targets for future resource utilization efforts. So as the dust settles, literally and metaphorically, scientists and engineers are forced to reevaluate their strategies. There's now an even greater impetus to map, monitor, and perhaps one day mine subsurface ice, rather than chasing the specter of liquid water on sunlit slopes. The hunt for Martian water isn't over, it's just gone underground. But this new perspective doesn't just affect where we go, it shapes how we travel and survive on the red planet. The machine learning study reveals slope streaks are more likely on slopes exposed to high winds and heavy dust deposition. This tells us that dust, not water, is the real architect of change on Mars. The planet isn't just a frozen desert, it's a dynamic, restless landscape where the smallest grains command the greatest power. This is both a warning and a challenge. Martian dust storms are already infamous for choking solar panels, corroding machinery, and swirling around the entire planet for months at a time. With the realization that millions of tons of dust are being moved by natural avalanches every year, engineers must step up their efforts to develop dust mitigation technologies. Imagine future Mars habitats protected by self-cleaning surfaces, or robotic bulldozers capable of stabilizing treacherous slopes. These innovations could become as vital as spacesuits or radiation shielding. But there's more, far more at stake than mere engineering. The idea that slope streaks are dry and therefore biologically uninteresting might tempt mission managers to deprioritize these sites in the search for life. That would be a mistake. The lesson of the Martian streaks isn't just about what they are, but about the power of questioning our assumptions. For decades, the allure of water shaped our expectations, funding, and scientific focus. Now, as the evidence tilts toward dust, we're forced to confront the limits of our own imagination. There's a broader ethical question that now looms over every Martian mission. If liquid water is nearly absent on the surface, does that make it safer or riskier for humans to explore? On one hand, less water means fewer places for Earth microbes to survive if accidentally released, relaxing some forms of protection. On the other, dry Mars may be even more vulnerable to our contamination, since even a single surviving microbe could dominate a new niche. The SETI Institute cautions, regardless of the formation mechanism, we must exercise extreme caution when exploring RSL sites. The potential for terrestrial contamination remains a serious concern, and we need to proceed responsibly. Even if RSL aren't watery, they are still windows into Martian processes we barely understand. They teach us that Mars is not static. It's alive with wind, dust, and hidden energies, forces that might one day threaten or sustain us. So, what are the practical takeaways for viewers, whether you're a student, a science buff, or someone who dreams of setting foot on Mars? First, embrace the spirit of scientific revision. Progress often means letting go of cherished ideas, no matter how enticing. This latest breakthrough in Martian research is a vivid reminder. Our best theories are only as strong as the evidence allows, and real discovery takes patience, humility, and the willingness to be surprised. Second, understand the power of big data and machine learning in planetary science. The ability to analyze hundreds of thousands of high-resolution images, to detect subtle patterns invisible to the human eye, is revolutionizing our understanding, not just of Mars, but of our own world. These skills aren't just for professional astronomers. Anyone with curiosity and some coding chops can dive into public data sets, contribute to citizen science, and even help solve the next cosmic puzzle. Third, appreciate the interconnectedness of planetary environments. What looks like a simple streak on a Martian hill is, in fact, a clue to deep processes, wind patterns, regional geology, even long-term climate change. By studying one enigmatic feature, we unlock insights that ripple outwards, influencing how we design robots, plan missions, and even think about the fragility of our own planet. And finally, remember that the search for life, water, or clues to ancient habitability hasn't stalled. It has merely shifted focus. Mars still holds secrets beneath its dusty crust, ancient riverbeds, ice-capped poles, and perhaps deep aquifers waiting to be tapped. As we wrap up, let's return to the question that lingers in every mind. Has the dream of finding modern life on Mars evaporated with the case for liquid water on its slopes? The short answer, no, not entirely. The odds may be slimmer, but Mars remains a world of surprises. Even if we find no living organisms, the planet's dynamic dust cycles, frozen reservoirs, and enigmatic history promise decades of discovery. As Christopher Edwards puts it, while the evidence strongly supports a dry mechanism, we shouldn't completely dismiss the potential role of subsurface ice. Even if water isn't directly involved, its presence beneath the surface could influence dust behavior and slope stability. The real scientific lesson? Mars keeps us honest. It forces us to confront what we want to believe, and then challenges us to prove it. In a sense, every dark streak on a Martian hillside is a testament to both the power and the humility of human curiosity. And here's a secret fact. Even as the world's attention shifts to other Martian mysteries, the sheer number of slope streaks as measured by machine learning, nearly 500,000, means there's far more movement and surface change on Mars than we once believed. These aren't just dusty scars. They're evidence that Mars is alive in its own restless way. So the next time you see a new Mars photo, look closer. Somewhere in that landscape, hidden in plain sight, may be the next clue that will rewrite what we know about the red planet, or even about life itself. If this video made you think differently about Martian mysteries, share your thoughts in the comments below. Are you excited by the new discoveries, or disappointed that water isn't gushing down Martian hillsides? If you have questions about the data, or ideas for where future landers should go, let us know. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the science that shapes our universe.